Nippon pulse motor, nano, and an electrolytic cap to do local bypass. That cap is important. Normally we use a capacitor based on the current and the voltage, but when the current is large, you may need the capacitor. I don't need the capacitor here. I'm only doing 2 amps. The power supply has plenty of capacitance and is a short distance from the capacitor. But if it's larger currents and a longer distance, you will need the cap located very close to the drive, maybe underneath a little bit. Yeah, this is the Nano miniature 24-volt power supply. I think it's 2 amps because I'm clipping out somewhere above 2 amps. And that's the tubular linear motor, Nippon pulse. So let's take a peek at that. So here's the Nano and the size of a postage stamp, 35 millimeters by 30 millimeters by 24 millimeters. A little bit taller when you stack a board on top of it with connectors. So I've got that wired up here. Love this CAD thing here. So here's the tubular linear motor, moving coil connected to the actually moving magnet here. The coil is stationary because the wires that come out don't need any strain relief. And there's a bearing in here which holds up the mass, and the rod magnets in the rod. Those are what move. Just a quick peek at this. It comes with the 0.1 micron encoder and making a 100 millimeter move. So I've got this one right here, and it's got low mass to start with, but it can reach some pretty considerable forces. Moving mass, load capacity, 45.5 kilograms. So I've got the 0.1 micron, so the speed is limited to 1,350 millimeters a second. That's hitting about a meter a second. Encoder A naught, B naught. There's an X and X naught on there too. Limit switches. We do a little wake and wiggle for algorithmic phasing. Resistance, large resistance. So at 2 amps, you do have considerable volts, but it's a low volts per K or volts per meter per second. So we can hit about a meter a second here. And there's some specky stuff on it. So what I did is I entered the motor information. It's a brushless linear, incremental encoder, 0.1 micron. There's like a 10 nanometer option too. Don't ignore your feedback. If you had a break or need controlled stop, the worst that's going to happen is you're going to pinch your fingers, but there is safe torque off or stow on this Nano, so you can use that. I entered the motor data, 30 millimeter magnetic pair length. At 14 newton meters of peak force, I reduced it for this power supply, but 3.5 newton meters at approximately 3 newton meters per amp, 4.2 newton meters per amp RMS. Yeah, 9 ohms, 1.3. I put the max velocity limit there because I don't want to overspeed the encoder. I'm not sure what encoder that is, but there's a blue glow on it. I got the current loop all tuned up, about 1 kilohertz. Velocity loop's tuned up with the velocity limit in there. Position loop, it's a linear motor, so higher PP seems to be okay. A little bit of integral in the velocity loop. And we can record the move here. I'm tracing the profile velocity, following error, actual current, bus voltage, nice solid 24 volts. Terminal voltage servo in the light blue gets up to almost a volt or two. Depending on your current, you got some large resistance, so some IR drop. But this current is maintaining for the acceleration about an amp 0.5 and getting little peaks of 2 amps. So probably going through the electrical cycles here, get a little bump out of it. But move and then settle and then move again. So pretty good, plus or minus a couple of counts. There's a 0, plus or minus a few counts on that. And I'm just running a demo CVM program here. So we'll take a quick peek at that. So on power up or reset, it'll wait for a second for the reset. I'm doing a 0 move distance just so I can wait for the thing to phase. I'll wait for 3 seconds. And then I do a homing, move out 100 millimeters, move back 100 millimeters, move out 100 millimeters, and then a conditional jump. There's no real condition, 0 always equals 0, so back to the home again. And we can see it's just doing a home to a hard stop here. So without halls, there's a little algorithmic phasing that goes on, but there is a HA option for hall effect. I'd recommend getting the halls so we can do the commutation without having to do the wiggle. And back to the Nano here. So besides being small, I mean this motor is 1.8 amps continuous, and probably has like 5 times for peak. I've got it set down to 2 amps. So with a larger mass, you can still get the acceleration. You just got to watch the duty cycle on it. So keep your duty cycle at less than 1.18 amps on average. And you can see how to do that using the scope. So you've got a typical move, 1.07 amps RMS, a little bit of dwell in there, and you get a little bit less. Just add that dwell there. Yeah, so about an amp RMS on average for this move here. No big mass. The duty cycle would have to extend out. So yeah, get the Hall effect sensors. I got the 5 amp Nano, 10 amp peak. That's the smallest current one. Of course, I'm running on 24, but this motor can handle a lot higher voltage. Plus, the IR drop at 10 amps, that'd be 90 volts. So we make a 180 volt Nano for like 150 volt supply. And then of course the large one, you could do over 5 amps all day. Maybe there's a bigger motor, but this is just an example of world's smallest servo drive. Just a little note on the connectorizing. So if you're using the Z option, that would be the little connectorized board. That's the development board. So there, going into the brown. So we've got the serial adapter for the Molex SCR-USB-M. So USB on one side, serial on the other. That just plugs right into the Nano board. There's a stow jumper. This one's CAN versus EtherCAT. Some blinky lights. And there's the stow bypass jumper. I've got that installed. That bypasses the safety circuit. So you can see this CX is a capacitor located close to the drive, and maybe 250 microfarads for every amp you use. Really, I should be using a cap here, but my ringing's probably not too high, so I'm not tripping things up here. But yeah, so there's a recommendation for 90 volts, 1,370 microfarad capacitor. That's a good idea. That's the HV, or the high voltage. That could be a higher voltage than the V logic. Of course, that should be like 24 or down to 9 volts. So 9 to 60, we don't want to over voltage that. So watch your regen, especially with moving a big mass around. And I've got the incremental encoder, AA not, BB not, twisted, shielded. There's a shield terminal on here. Yeah, so these screws are just the shipping screws. So you could mount the heat plate to a larger piece of metal and pull the heat out. Thing's not even going to get warm at like 5 amps RMS, so don't worry about it until your currents get much higher. But yeah, here's the little board that goes on top, and I've got the encoder connected in. It could be an absolute encoder like a BIS-C. This is the ARM version. The Plus version will have all the fancy feedback. AA naught, BB naught, XX naught could hook up here to J7. There's the Stowe bypass jumper at J16, and I've got the V-Logic powering it up here at J19, HV-COM, V-Logic on pin 2. I'd recommend not wiring that backwards. You're going to short your supply out and maybe damage something, but I swap the wires and now it seems to work. These terminals here are going to the frame ground, and I've got the protective earth or frame ground connected up to P7 or P1, which connects the frame components, including the heat plate, the screws, and these posts to the earth. And then you can use these posts to bring your shields, like the encoder shield can go over to a post. Your CAN cables can go to a post. And motor UVW or a brush motor UV. So you could, for safety, you could turn off the high voltage and keep the keep alive. And dual encoder feedback, you could have incremental and this. Not sure why you do that on a linear motor, but this one's CAN, so CAN high, CAN low, CAN ground with a shield, or no shield because it's just a twisted pair typically. And Halls are good, UVW plus 5 and ground is another connector for the Halls. And the RS-232 again comes in this 3-pin Molex connector for the Copley serial cable. And then you could use the Copley CAN adapter here too. And again, at 1 to 2 amps, this thing's just, it's going to just be warm. It's not even going to heat up. So 5 amps RMS, that should be fine without a heat sink. Above that, you might want to consider mounting the heat plate to the frame. And there should be an image of mounting the heat plate to the frame in here. But the bottom is a copper gold ENIG, which is twice as conductive as your normal aluminum substrate. And just, yeah, don't get the heat sink. Just mount that aluminum plate to your frame of your machine. And you can see that gold copper ENIG plate there. The screws come down, tap a couple holes, and bolt it right to your frame. As the infinite heat sink, so even if you did 35 amps continuous, 70 peak at 90 volts, you could pull all the heat out. Okay, thanks for watching.